All right, trees. So we're going to learn about trees. So it's going to be fairly high level, and we're going to learn some terminology about trees. Okay, so the first thing is trees are, they're data structures, but they're nonlinear data structures. And what I mean by that is when you're at a list, or a stack, or a queue, if I put you at the beginning of wherever that is for that data structure, and I ask you what comes next, there's an answer. But trees are nonlinear. It gets a little hairy. And trees are usually good for some hierarchical data of some sort. So maybe like a family tree, some maybe inheritance. You know, think of inheritance like even in computer science, like when we're programming that hierarchy of inheritance in our objects. Or maybe the file systems in a computer. We can kind of think of these things as a tree, a decision tree, table of contents of a book, the information on this slide. See how it's kind of like tree might be at the top, and then we've got like, well, you'll see in a second, and you'll probably be able to make sense of that. So here's a silly example of a file system on someone's computer, right? At the top, we've got like C, their C drive. And then they might have a folder under there called Documents and Settings, maybe another one called Program Files, and then My Music. But under Documents and Settings, we've also got Desktop, Favorite, Start Menu, and so on. So we can, the point of this data structure is a way to just kind of conceptualize and hold on to information. We're using it for us to keep track of things the way we like. Just a warning as we go, there's going to be a lot of definitions here. But don't get too worried about definitions. I always hated learning definitions, especially in computer science. Part of the reason I like computer science is there wasn't that much memory involved. But the good thing with the definitions for trees is a lot of their definitions are kind of intuitive. You'll see what I mean. So, okay, a tree, it's a collection of elements of some type such that it's empty, or it has a distinguished element called the root, which descends 0 or more subtrees. It's kind of like a recursive definition. So a tree is either nothing, which is weird to think about, but that's what we're saying it is. So a tree is either nothing, or it's a root where it has some number of descendants, 0 or more descendants, that are also trees. Yeah, it's recursive. So here's an example. There's the root, and it has 1, 2, 3, 4 subtrees. And in this case, each of those subtrees are trees because they have roots and then have subtrees and so on and so on and so on. So recursively, it's a tree. This is what we call the root. This is what we call interior nodes, and these are leaf nodes. So leaf nodes are the one at the bottom that have no one coming out of them. Root is the one at the top, and computer scientists are funny. We put the roots at the top of our trees, not at the bottom. They're kind of upside down. And interior nodes are the ones that aren't the root or the leaf, the leaves. Okay, a node, it's an element in the tree. So that would be like the squares here. An edge is the connection between nodes. So those would be the lines that were connecting the squares. The root, the special distinct element at the origin of the tree. Trees only have one or no root nodes, because remember, an empty tree is a tree, and I guess in that case it doesn't have any root node. But there can be at most one root node in any given tree. If it has more, then we don't have a tree. A leaf node, a node without any edges to a child node. More on what a child node is in a moment. Interior nodes, not a leaf node. Empty tree, a tree that has no nodes or edges. So I could tell you right now is, oh, I drew a tree on the board. There's nothing there, but by our definition, that would be a tree, I guess. Okay, a parent or predecessor, that's like going up. The node above, any given node can have at most one parent. But a parent node, or any given node, can have multiple child nodes. Those are the ones that come out of the tree. We can have 0 too many. A sibling, nodes that have the same parent, ancestor, a node that is the parent or the parent's parent, and so on. A descendant, same idea, but down. So here we go, we got a lot. Can a leaf node have any children? No, because that's against the definition of a leaf node. So okay, and here all the squares are nodes. That one at the top, that's the root node. The black ones are the leaf nodes. The light blue ones are the internal nodes. The blue lines, those are the edges. Notice that the root is going to be the ancestor of all nodes. And all nodes are descendants from the root node. That's just going to be that has to be true. So I mean, there's a lot going on here. Can the root have a parent? No. Excluding the root, how many parents does each node have? Well, at most one. Okay, a path, a sequence of nodes and edges leading from one node to another. So that would be saying, we go back here. Oh, I want to go from maybe this node to the root. What's the path? Well, I go like there, 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 right? The length of a path, that's the number of edges, and I need to emphasize this because a lot of people, it gets confusing. Because you always think, wait, do I count the node I start at? The trick is, don't think about counting the nodes, think about counting the edges. So if I asked you, if we were at this one, and I wanted to know the length to the root, what is it? Well, 1, 2, 3. If you count the edges, you're safe. Otherwise, you might go like, wait, 1, 2, 3, 4. Wait, do I count the one I'm starting at, or what? Just, if you count the edges, you're safe. Just count the edges, you're good to go. The length, or pardon me, the height of a tree is the length of the longest path from a root to a leaf. So that is what we would call the height of a tree. Trees can be unbalanced, where you have some weirdly long path over here, but short ones over there. But the height of that whole tree is going to be the height of the length of the longest path that exists from root to child within the tree. Not the longest path that exists within the tree. The root needs to be the start or end, and then a leaf needs to also be included. So what is the length of this path? Well, I didn't emphasize path, but whatever. What is the length, or what is the height of a tree with only a root? Oh, okay. What is the length of this path? I didn't emphasize one, I guess. Do I? Oh, here we go. Okay, here's what I'm asking. I guess I should have drawn the red circles earlier. What is the length of that path from red one to red one? Or red circle to red circle? Well, 1, 2, 3. 3. Why? There's 3 edges between. What is the height of a tree with only a root? Well, based on what we just learned, what would that be? Remember, the height of a tree is the length of the longest path from the root to some child. Or to some leaf node. So the height of a tree, well, I mean, I guess, if I'm only counting edges, and there's no edges, the height of a tree with nothing in it would be what? It'd be 0, right? Because there's no edges to count. So I guess a tree with no root, or pardon me, with only a root, has a height of 0, which is kind of funny to think about, but that's, by our definitions, that's what it is. Then, weirdly, what's the height of a tree with nothing in it? Well, we're just going to say that's -1. An empty tree has a height of -1. Kind of weird to think, but that's what we're going to go with. A level of a node, well, that's the number of edges between the root and the node. So, basically, this is what it is. Level 0, the root is going to be level 0. There's only one node in level 0. And then going down level 1, level 2, level 3, and so on. what is the level of a node in relation to the length from the root? Well, it's going to be like the same. What's the next question? What's the height of the tree in terms of its levels? Well, the maximum level will be the height of the tree. It just has to be. So we have level 0 at the top, then the 1, 2, 3, 4 on the next layer would be level 1, then the 1, 2, 3, 4, 5 on the next one, level 2, and then level 3 are the black ones at the bottom, 1, 2, 3, 4. The height of this one's 3. Why? Well, because that's the longest path that exists. You can't find, the longest path from root to some leaf node that exists within this tree. You can't find a longer one from root to leaf node. Obviously, the longest path you can find in this tree would be like from a leaf to a leaf. So 1, 2, 3, 4, 5, 6. That's the longest one I can find. 1, 2, 3, 4, 5, 6. Yeah, there's 2 paths of length 6, I guess. No, 3 paths of length 6. Can you find them all? Subtree of a node, a child node and all its descendants. So that would be a subtree. The subtree is itself going to be a tree. What I mean there is, if I have a tree, maybe it looks something like this. This tree has 2 subtrees, this and this, which are themselves trees. Also note that this one here has no children, but it technically, by our definition, has 2 subtrees, but the subtrees are like empty. There's nothing there. It's like null, I guess, if we were to code this. But those are also a tree. So this actually has 2 subtrees which are empty, but empty things are trees. So there we go. These are all the subtrees in the example we were playing with. And there are more technically because, I mean, each subtree, like this tree here, this subtree has subtrees. This is the subtree, this is the subtree, and then this is the emptiness. Well, that makes it look like another node. But like, the emptiness over here is also a subtree. So subtrees have subtrees have subtrees. Like, you can really see how the recursion pops up here. Degree or arity of a node, that's the number of children a node has. Not the total number of edges, I guess, it's the number of children a node has. The degree of the tree is going to be the maximum degree of all the nodes. So in this case, this looks like it's going to be 2. But in our example, what do we have? What's the degree of this tree? Well, you look at all the nodes, find the one that has the maximum number of children, and then the degree of that tree is going to be that. So in this case, it looks like it's going to be the root, which has 4 children. So the degree of this tree is 4. Cool. Well, that's it for the summary of trees. It was just a lot of definitions. And trees, like the way I described it, was very general. It's just a bunch of definitions, very general, and we're going to start talking about a more specific type of tree. I want to be clear that you're going, like at this stage, the tree stuff, important, very important, but really, that stuff is going to come up a lot more next year, in second year. So right now, know it, learn it, but there's going to be a lot of holes and gaps that I'm deliberately leaving because things are going to get too complex that I don't want to start bogging you down with at this stage. So bear with me. So now we're going to talk about binary trees. And if it wasn't, well, let's see. Okay, what are binary trees? We're going to talk about some tree traversals, which are interesting. And we're going to look at a very incomplete binary tree implementation. The incomplete part is because I don't want to scare you. There's going to be too many catches that I don't want to deal with right now, and neither do you. You'll have a lot of fun with it next year. So, binary tree. Okay, remember a general tree is a tree where each node has any number of children. So an n-ary tree, pardon me, is a tree where each node has no more than n children. So in the previous example, it was like a 4-ary tree. Because there was only 4 children. A binary tree is a tree where no node has more than 2 children. The example that I drew on the board a moment ago and have since erased is a binary tree. It's like a two-ary tree. A tree of 2. The children, if they exist, now this is an important thing about binary tree, is it's positional. The fact that a certain node is on the left or the right is meaningful. So each node has a left or right subchild. They might not exist, but a left and right, and we're going to refer to them as left and right accordingly. So if we've got this is the left, and this is the right subtree. This is the root. And of course over here, there's 2 empty subtrees, but this node still has a left and right attribute. So left, even though there's nothing there, and right. I could also have something like this where that one exists. So the left exists, but the right does not exist. And remember, I'm drawing the little like 2 lines to mean nothing. It's like null, empty. That's a binary tree because each tree has 2 children, a left and right. It matters that the left and right, and the children have to be trees themselves. This is a tree, this is a tree, this is a tree. Nothingness is a tree, apparently. This is a tree, this is a tree, because this has a left and right, which is nothing. And this is a tree. So, I mean, everything's a tree. Take a second and think, okay, this is a binary tree. What would, like a unary tree be? Take a second and think about it. It's not too complicated. It's kind of like a trick question. And you know the answer, but what would a tree look like if it only ever had 1 child? Think about it. So, the recursive definition of a binary tree. If you couldn't tell, we're obsessed with recursion now. So, a binary tree is an empty tree, or a tree that has a root whose left and right subtrees are also binary trees. In our example, that's the case. So, that's a recursive definition of a binary tree. That's it. That's all we need. If it seems too simple, well, that's it. We're lucky. It's either nothingness is a binary tree, or a root, which is the top of some tree. Remember, this is the root of the whole tree. This is the root of this subtree. So, it's either an empty tree or a root with a left and right subtree that are also binary trees. And that follows through this on that example. So in a binary tree, it does matter which is left and which is right. It's positional. Here's an example of a binary tree. If you follow that recursive definition, we're fine. We've got A. Well, there's a root node, and it's got a left and right subtree. Are those binary trees? Well, we can investigate. Okay, let's check out B. B, okay, we got a root node. Is the left and right a binary tree? We would just recursively go down, and if we do, we would answer yes to everything, which would therefore mean that this is a binary tree. So remember with list traversals. With list traversals, it was easy. This is what I was just talking about a moment ago when I was talking about, if I gave you a list and said, okay, here's the head, go to the next one. Where do you go? You've got no other option other than, okay, from that light blue to green. Then what comes next? That teal color. Then what comes next? The black color. What comes next when we're done? There's no ambiguity of where to go next. It's easy. So linear data structures are great for traversals. They're simple. There's no questions to ask. If I gave you this tree, and I say, okay, what comes next? I mean, it depends. We've got 2 options. I could go to B or C. I don't know. So when I say traverse a linear data structure, it's easy. When I say traverse a nonlinear data structure, we have to be more specific. Well, how do you want me to traverse it? Because it matters, it depends. So let's have a look at a couple of examples. We're going to look at pre-order, in-order, and post-order traversals. The name pre, in, and post are going to become very important in remembering these traversals. By the way, I love these traversals. These are things I love to include on exams and whatnot, I don't know. But pre-order, in-order, post-order. If you pay attention, you'll never forget how these work. Here's three, and we're also going to look at another one called level order, which is, I don't want to say more complex. If anything, it's easier to wrap your head around, but kind of harder to code, because the first three are very easy to do recursively, and the last one, it's more complex to code. And remember, a lot of time that recursive code is beautifully simple. So, pre-order traversal, here's the algorithm. Start at the root. Visit the node, visit, whatever that means. In our case, when I visit a node, I'm just going to print out the node's label. Visiting the node is it depends what we're doing. Are we searching for a value? Are we printing out the value? Are we just seeing if it is a binary tree? Whatever. We're visiting the node and doing something with that node. Then, I'm going to do this. If the tree is not empty, okay, visit the root node. I just said that. Print in our case. Then we're going to do a pre-order traversal on the left subtree. And then once that's done, I'm going to do a pre-order traversal on the right subtree. That's it. This is it. If you think I'm skipping steps, I mean, I'm not really, because remember, Recursion lets us be really lazy. All I'm doing is print out me, then do a traversal on the right subtree, left subtree. I'm getting confused because my right, your left. Visit me, print out the value. Go to the left subtree, go to the right subtree. That's it. That's it. If it seems too good to be true, you'll see. Oh, yeah, left subtree. So here we go. Here are the rules. Let's think about it. We start at A. We are currently at A. I'm going to use my cursor to kind of do some bookkeeping for me. So we are at A. The rule says, visit, in our case, we're just printing it out. So, I'm going to visit A. I print out A. Great. Then what does it say to do? Okay, just do a pre-order traversal on the left subtree. Okay, great. So I go to the left subtree, that's B. So now I'm at B. I start over. This is a new frame. This is a new thing on the call stack. I visit the root of that subtree. So I print out B. Okay. Then what? Oh, do a pre-order traversal on the left subtree. Okay. Go to D. Start at the beginning of the recursive function. This is a new call frame. What do? Well, print out what's there. D. Go to the left subtree and do a pre-order traversal on the left subtree. Ah, it's empty. We don't do anything. There's nothing to print out, so we're done. So now, we finished doing the pre-order. So moments ago, we printed out D. Then we wanted to do the pre-order on the left subtree, and we finished it. We come back. Now what? Pre-order on the left subtree, or right subtree. Okay, great. So what I mean is, we printed out D. We went to the left subtree, there was nothing, we returned. Now, because we finished this part, we got to go here. So we go print out H. Print out H. Go to the left subtree, there's nothing there. Go to the right subtree, nothing there. Return. Now we're done printing out the whole subtree of D. So we return to B. Now we got to go to E. The right subtree of B, because we just finished the left subtree of B, which was the D one. So E, print out the left and right subtrees of E, they don't exist, we return, we go back to A. Now we're at A, which means we just finished printing out the whole left subtree of A, meaning now we need to do the pre-order traversal on the right subtree. Okay, so we go to C, print out C, go to the left, print out F, go to the left, print out I, go to the left, nothing, return, go to the right, nothing, return to F, go to the right, nothing, return, go to C, nothing. Oh, not nothing. Go to C, go to the right, print out G. Return, return, we're done. Let's make sure I'm right. This is just a whole crazy picture. It's showing exactly what I did a moment ago. A, B, D, H, E, C. A, B, D, H, E, C, F, I, G. Haha, I did it right. Good. Pre-order. Node, left, right. Pre. So let's look at in order. Start at the root. If the tree's not empty, do an in order traversal. Then print out the current node. Then do a pre-order or in order traversal on the right subtree. So with pre-order, I dealt with the node before anything. Then I went to the left, then I went to the right. Now with in order, I go to the left, then handle me, then go to the right. I'm going to erase this because we're going to do it again, but with the in order traversal. So notice that this visit the root node, the print part with pre was at the beginning. Pre-beginning. Now here it's in between, in order. I wonder where post order will go. Well, we'll find out if you haven't figured it out already. But we're going to do in order first. Let's see if I can get all these right the first time I go through. I always mess up. Let's see if I can do it right this year. So, I go to A, I don't do anything. I go to the left, I don't do anything. I go to the left, I don't do anything. I go to the left. Okay, I'm at D, and I just went to the left. There's nothing there, so I return. Now I deal with D. Then I go to the right. I go to H's left, there's nothing there. Return to H, print out H. Go to H's right, there's nothing there. Return to H, return to D. Now I finished B's left subtree, the subtree that started at D. And I return to B. Now I can print out B. Then I go to the right subtree, go to the left, nothing there. Return to E, print out E. Go to the right, there's nothing there. Return, return. So now I finished the B subtree and I return to A. Now I can print out A because I finished the left subtree. Go to the right. Go to the left. Go to the left. Go to the left. So we're at I, we go to the left, there's nothing there. Return to I, print out I. Go to the right, nothing there, return. Return to F, so we finished the left subtree of F. Now we can print out F. Go to the right subtree of F, there's nothing there, return. We're at C. We finished C's left subtree because we returned back to C. Print out C. Go to the right, go to the left. G doesn't have a left subtree, return to G, print out G. Go to the right, nothing there. Return, return, return. Did I get it right? D, H, B, E, A, I, F, C, G. Yes, so far so good. I'm 2 for 2. It's the next one I always have a hard time with, so we'll see if we got it. So post order. Remember, before, with pre, the printing out of the node happened before. Before. Then within order, it happened in between. Post order, I'm willing to bet it's going to happen after. Let's see what I've got. Yeah, perfect. It's exactly what I thought. Go to the left, deal with it. Go to the right, deal with it. Then print out what's at me. Remember, I'm here again. I'm saying, oh, dealing with the node is printing it out. Dealing with the node is whatever you want it to be. I'm just printing it out for the sake of showing you how the traversal is working. But we'll see more examples of what I mean about whatever we want to be soon. So this is the one I always mess up. Let's see if I can get it right. We got to go to the left, then the right, then deal with the node. I would encourage you at this stage to pause the video, grab yourself a scrap sheet of paper and see if you can get it yourself. So, okay, we're at A, go to the left, go to the left, we're at D, go to the left, there's nothing there, return to D. Go to the right, so now we're at H. Go to the left, nothing there, return. We're back at H. Go to the right, return, print out H. Okay. Return to D, now I can print out D. Return to B, but we need to do B's right subtree first. Go to E. E's left doesn't exist, E's right doesn't exist. So now we print out E. Now when we return to B, we're done all of B's left and right subtree, we can print out B. Return to A. I've only done the left subtree. I still need to do the right subtree before I can print out A. So I go to C, go to the left, I'm at I. I's left doesn't exist, I's right doesn't exist. I can print out I now. Go to F, go to F's right subtree, doesn't exist, return, print out F. Return to C. Don't do anything with C yet though, I still gotta go to the right. I'm at G. G's left subtree doesn't exist. G's right subtree doesn't exist. Return back to G. Return to C. Return to A. Did I get it right? This is the one that matters. H, D, E, B, I, F, G, C, A. Yeah, I got it. Good. So notice how simple the traversals are. You only need to remember one traversal, one thing of code, and then modify it. It's with the pre, in, and post. You should be capable of remembering that. Is it empty? Otherwise, if it's pre, me, left, right. If it's in, right, me, left, me, right. Post, left, right, me. That's it. That's it. It's magical. Pre, before, in between, and post, after. So now the level order traversal, here's what it is. Visit the nodes at each level in order left to right. That's it. It's a simple one to wrap your head around. In this, it's A, B, C, D, E, F, G, H, I. Start at level 1, print out all the things in level 1. It's just the root, it's A. I suppose I should erase this so you don't get confused. So print out everything at level 1, left to right. Okay, that's it. Now go to the, pardon me, I said level 1, I meant level 0, A. Level 0, A, print it out. Now go to level 1, left to right, B, C. Now go to the next level, D, E, F, G. Now go to the next level, H, I. Go to the next, oh, no, we're done. Now what's the code here? So there is a recursive one for this, but it's not pretty. So here's how we're actually going to do it. We're going to do it with a queue. And it's actually really simple if you do it with a queue. But here it is. Start at the root, add it to a queue. So here's my queue. I'm going to draw my queue like this. I start at the root, it's A. Then I say, well, the queue's not empty. Take something out of the queue, add its left and right, like deal with it some way, maybe I'll print it out. Then add the left subtree to the queue, the root of the left subtree to the queue, so the left child, and then the right child to the queue. That's it. So take something out, deal with it, take its left subtree, add it to the queue, right subtree, add it to the queue, and just repeat till the queue's empty. So here, we added A. I take out A. So I dequeue A, and I print it out. And then I add A's left and right subtrees. So that's B and C. So I add B, and then I add C. Okay? Is the queue empty? No. Dequeue it. So I've got B printed out. Add B's left and right subtrees. Okay, that's D and E. Great. Notice that Like, I added D and E, but I'm going to have to deal with C before. So I take out C. Great, I'm going to erase all this so I can give myself a little more room, print out the C. Add its left and right subtrees, well that's F and G. Okay, is the Q empty? No. DQ, take the D out, print it. Add its left and right subtree, well there is no left subtree. Add its right subtree, H. Is the Q empty? No. DQ, well it's E. Print it out. Add its left and right subtree. They don't exist. Is the Q empty? No. DQ. F. Print it out. We're going to remove my Q, but bear with me. Add its left and right subtree. Well, only the left subtree exists, so it's I. Okay. Is the Q empty? No. DQ. Print it out. Add its left and right subtree. Well, they don't exist. Whatever. Go to H, because I'm DQing, because the Q's not empty. Print it out. Add its left and right subtree, they don't exist. I, DQ. Deal with it. Left and right subtrees, they don't exist. Is the Q empty? Yes! Oh, we're done. The Q will only be empty when we're done, and that's it. And am I right? A, B, C, D, E, F, G, H, I. Good, there we go. So it's really simple to do with a Q. If we switch the data structure to a stack, I wonder how it would have worked. What would have happened? Huh. So, just by changing the container, we'll change the order of the traversal. So we used a queue, we got this level order. If we change it to a stack, it would affect the order. Now with recursion, we actually used a stack. We didn't use a stack that was like coded. We used the system stack. We used it to our advantage. Recursion uses the system stack, those call frames being pushed and popped. But I could write it with like for loops and whatnot, using a stack data structure to do similar things. So, iterative traversal, it's going to look something like this. Create a container, put root in the container. Well, the container's not empty. Remove from the container, deal with things from the container, add the children to the container, repeat until the thing's empty. That's it. So, consider we have a binary tree with n nodes. Pay attention here to what I'm defining n as. N is the number of nodes. So, for any of these traversals, how much work are we going to have to do in terms of n? So here I'm looking at in order, but I can do pre-order, post-order, it doesn't matter. The trick with doing the analysis on recursive things is to think, how many times is this function going to be called? How many times, how much work is going to be done? Well, here's the thing. For every single time this function is called, at most, how many more function calls are there? Well, there's two. How do I know? Well, if this function gets called, I can call it here and then here again, at most. It could be empty, which means I don't call it again. So that means for every node, because I'm going to start with the root, and then the root's going to make two calls for the subtrees, and then two calls for the subtrees, and two calls for their subtrees, and so on, how much work is going to be done? This might sound familiar to what we talked about last time with recursion, when we talked about Fibonacci, when we talked about Towers of Hanoi and how much work there was. And we got really scared about the amount of work being done. But there's a key difference here. Here, if I have n nodes, there can be at most 2 calls for each node. 2 times n. 2n. That's it, which means it's going to be order n. in terms of n, where n is the number of nodes. But you might be saying, last time we had 2 to the n. Why is this you get the idea that for each node, there's going to be 2 calls, right? So there's going to be 2 times n calls. I get that. I mean, you can even think of it even simpler. If I wanted to traverse this tree and there's n nodes, I'm going to have to put my finger on each node, no matter what. And if there's n nodes, how many nodes am I going to have to put my finger on? All of them, n, linear. But why is it that last time, when talking about Fibonacci and towers of Hanoi, which kind of grew like a tree, was it 2 to the n? And there's a key difference there. The difference is, what is n? In our case, n is the number of nodes. But with towers of Hanoi and with Fibonacci, n was actually more analogous to the depth of the tree. So if n was the depth or height, height of the tree, then we're going to have that 2 to the n relationship, where n is the depth. Because at each level in the tree, if we have a full binary tree, it's going to grow 1, 2, 4, 8, 16, 32, as we go down in levels. So Fibonacci, when calculating the nth Fibonacci number, we had to go down n levels. Towers of Hanoi, we had to go down n discs, like 1 level for each disk. Where here, n is the number of nodes. Big difference. So, when talking about the amount of work being done, we need to be careful. What is n? What is the input? So if it's the number of nodes, it's linear based on that. But it's not going to be linear based on the depth of this tree. But I didn't ask about the depth of the tree. So how might we implement it? What would we want? Well, we're probably going to want a way to add elements. And you might be asking, well, where do I add the elements? There's a lot of options. Do I add it like at the root? Do I create a new root? Do I just go to the most shallow subtree? Do I fill left to right? I mean, the way you add the nodes, the way you add elements, kind of depends on what you want. So that's going to be complicated. And same with removing things. Where do we remove from? Do we remove from the top, the middle? It kind of depends on what we want. And that's where things get hairy. And those are 2 examples of things we're going to ignore for this general binary tree right now. But we're probably going to want to know, is the tree empty, get the size, and maybe do the traversals through the trees, right? So if I've got this tree, I might say, well, how many nodes in this tree, do the traversals and whatnot. We can do those, and I know we can do those because we just did it. But if I said add a new element x to this tree, you're going to say, but where? Or remove something from this tree. Well, but where? I mean, those aren't trivial things to ask. So, yeah. Similarly for remove. Also, so if I said remove h, okay, maybe we could code that. But what would I do if I said, okay, remove a? Okay, so you got to get rid of a. But that's the root. We're going to run into big trouble if we just remove a. So we're going to have to do some sort of shuffling around to address this situation properly. So, but we're going to be lazy. That's next year's problem. So here's what we're going to want. We're going to want to how about remove left subtree? We could do that maybe. Remove right subtree. Remove all elements from the tree. Determine if a tree is empty. Get the size of the tree. Ask the tree if it contains a certain element. Find, return a reference to a specific target if found. So think about the list. We did these similarly for a list. And then an in-order traversal, pre-order traversal, post-order traversal, and a level order traversal. We can code those things up because we already saw the code basically. We just have to turn it into C++. So we'll use a linked structure of nodes. And we're going to use count to keep track of how many things there are. These are going to be the attributes. But you might remember that the nodes we used before only contained the linear nodes. The linked nodes before only had 2 attributes. It had a next and the data. So we can't use those nodes, but we could create a new node, a binary tree node or something, where it's got 3 attributes. The data, the left and right. Why not? So we'll do that. So yeah, I've just said that. Great. That's the idea. That box may or may not be a pointer. I don't know. We're going to want to make it generic. There. That's it. That's the header. And the rest of the code, fairly straightforward. Constructors, whatever. Get left, set left, get right, set right. Get data, set data. That's it. Simple. So that's our binary tree node class, fairly straightforward. So now we're going to use those to build our binary tree class. Constructor's going to be straightforward, nothing crazy, just start with count nothing, root's going to be nothing, a tree will start as empty, let's say. Our copy constructors, those can get hairy, but it won't be too crazy, I hope. And then our deconstructor, that'll be fun, but we're going to have to delete all the nodes. Remember, we don't have to delete the data in the nodes because the data isn't the tree's responsibility. That's whoever created that data's responsibility, because that data may or may not be in dynamic memory. But the nodes themselves are going to be our problem. We're going to have to delete those if we want to delete the tree. But we'll be able to do find and traversals. And we're going to go to the scary bits because that's next year. So, let's say we want to search the tree for a specific target. How do we do this? Think recursively. And I'm going to give you a big hint. You may have actually already seen the code, but you would have to modify the code just slightly from what we saw before to get it to work here. How about this? I'll look at a node. If that node is nothing, did I find the thing I'm looking for? No, that's obvious. If the node contains the thing I'm looking for, then I'm done. I found the thing I'm looking for. I'll just return like, here it is. But if the node is not nothing, null, and does not contain the thing I'm looking for, well then I'll just look for it over here and over here. In the left subtree and in the right subtree. That's it. So let's see. So if it's null, return nothing. If the current's data, get data, I guess, should have had brackets there, parentheses. Get data is target, then return cur, because I want to return the pointer to the node that contains the thing I'm looking for. That's what find's going to do. So if the current node contains the data I'm looking for, I'm done. That's easy. But do a search on the right subtree. Oh wait, let me take a step back. Do a search on the left subtree. If left subtree is a null pointer, that means I didn't find it. Let me put it this way, I'll give you an example. 4, 6, and 2. Here's what I'm going to do. I started here. Is this a null pointer? No. Well, let me do one more forward here to show you what the last line of code is. It should be pretty obvious. Return 10. Okay. If you don't believe me, I'll demonstrate. We've got the root. Is this a null pointer? No. Let's say I'm looking for 2. Is 4 equal to 2? No. Again, do note that the cur get data should have parentheses after. That's a typo. Is 4 equal to 2? No. Okay, great. Then I say, call find on left. On get the left. Okay, so I call find over here. Is this null pointer? No. Is 6 equal to 2? No. Call it on left. Go down here. Is this a null pointer? Yeah. Return null pointer. Great. So now temp is equal to null pointer in our example. And I say, okay, is temp equal to null pointer? It is. So I need to search the right subtree. Okay, I go here. I get the result, put it in temp. It's going to be null pointer. I return null pointer to here. So because this got null pointer, it means that the thing I was looking for must not be on the left subtree. That's what it means. So now we're back up here in this data frame. So that means we just finished searching the left subtree. So temp is null pointer. Is temp null pointer? Yes. We go here. Is this a null pointer? No. Is 2 equal to 2? Yes. Done. Return cur. Boom. Return cur. It's 2. Great. I searched the right subtree. What does temp become? Temp will be a pointer to the node containing 2. Return temp. We're done. If I was looking for 3, I would just go here and be like, okay, 2 is not 3. Search the left. Not there. Return null. Because it's null, I need to search the right. It's not there. Return null. Return null. And this is just going to return temp, which is null. That must mean, if this returned null pointer in the end, that must therefore mean that the thing I'm looking for must not be in the tree. If you don't believe me, scratch it out with some piece of paper and a pencil, and you'll just make it make sense. This is critically important. Often we like to have these little helper functions to help with some setup for these recursive calls. Because maybe I would want to call it on the tree itself, and I don't want to have to give the root of the tree to the function. I'm going to want a helper function. So maybe what I'll do is I'll call find on the root. And I guess in my example, if cur is null pointer, I'm returning an exception. I'm throwing an exception. Why? Because I decided to do it that way. I don't know why, but I just decided to. Otherwise, I return the data. Cool. That's it. I return the thing of type T I was looking for. Cool. So this helper function is really simple. Pre-order traversal, that's it. All it's going to be is, if current's not null, print out the data, do pre-order on the left, do pre-order on the right. And then I've got a helper function that just calls it on the root. A lot of people are left scratching their heads saying, well, why would I want this as a helper function? Like, what's the point of this helper function? I could just call it. Imagine I have a tree object. I've got a pointer to a tree. It's called my tree. I want to say, my tree, do pre-order traversal. If I called underscore pre-order, by the way, the underscore, it's going to be private. If I called pre-order, I'm going to have to get the root of the tree in order to call it. Where if I've got this helper function, it just automatically calls it on the root for me. Because otherwise, find needs a pointer to some node to start. And we want to start with the root. So I would have to say, like, my tree, find my tree's root to start as the parameter I'm passing. We're here with pre-order, it just calls it for me. It's to save ourselves a little bit of time and headache. In order, look, it's the same. It's the same. But in this case, it looks like I'm doing some string building, which is interesting. A little different. I'm getting a pointer to a string and then I'm appending to it, where before I was just printing it out. Why? Just to show you that I can do it a little differently. So again, note that in order actually takes another parameter, the pointer to the string that I'm modifying, which is neat. You could have done in order exactly the same as pre-order where you just printed out the values, but I liked the idea of returning the string, just because. So here, in order, has a little bit more setup to do. Create the string, give a reference to that string, and then keep adding to it inside the recursive button. And in the end, return the order that maybe I'll print out. Level order. I'm just going to skip ahead. Here we go. It's the same as before. We're going to do string building again. But what do? Create a queue, get a pointer for current node, and add cur, which is going to be, I guess, the root when we start it, because down here is the root. And then we enqueue, or we dequeue, pardon me, well the queue is not empty, DQ, append it to our string, add the left if it exists, add the right if it exists. We're done, but we have to delete the Q when we're done. That's it. Now deleting, well, we could do this. If the tree exists, delete the left subtree, delete the right subtree, then delete the current node. That's what delete will be. Do I have it? Oh, I love this. It's so beautiful. I love it. My deconstructor will call the function delete tree. What does delete tree do? If the node exists, the node is not null, delete the left subtree, delete the right subtree, then delete myself. It's recursive and it's lovely. Look how beautiful that is. It's so simple. And that's it. Now, I realize I did blitz a little bit through some of these things, so take your time and go back. But this code right here is effectively the code that I showed you before, but before it was just like the high-level explanation of the pseudocode. Here it is in C++. A lot of people, I know right now you're watching the video and you're still scratching your head, what's the point of creating these helper functions? Don't worry too much. They'll become a little bit more obvious once you start using this code a little bit more. So for example, in assignment 4, it'll become a little bit more obvious. So don't worry too much and start freaking out that you don't remember or get what's going on there. The important bits are the not helper part. It's the recursive functions. And if you're having a hard time with the difference between my pre-order and in-order, how with my pre-order I was just printing out the values. See? Just see out, get the data. Just printing it out. That's it. But the in-order was a little bit more complex because I was doing string building. Well, the only difference is here, I'm also including a pointer to some string somewhere. So I've got a string that exists somewhere. I call the function. I append it to the string the current node's information. I don't know, X, right? Make a recursive call on the left. Oh, get the, Y. So I'm modifying some string somewhere else, and then in the end I'm returning that one string. Why did I do it that way? Because I could. If you're struggling with that, take your time, see if you can figure that one out. Anyways, that's where I'm going to end it for now, and then next time we'll talk a little bit about binary search trees, which are pretty cool.